We've been discussing string theory, but last week Lilia also introduced you to 11-dimensional supergravity, which we also discussed at the beginning of the lecture in a different form, because at the beginning of the course we discussed the dimensional reduction of this theory on toroid all the way down to 4 dimensions. We didn't say that it was that, but we discovered in 4 dimensions that there was n equals 8 supergravity as the maximal supergravity with how many supercharges? It had 32 supercharges in 4 dimensions. Well, that's the beauty of talking about supercharges and why people like to talk about that, which is that the number of supercharges doesn't depend on the number of dimensions. 32 supercharges in 4 dimensions means n equals 8 supergravity. But 32 supercharges in 11 dimensions means what? N equals 1. So we shouldn't even write it, but because it's the only theory that we know in 11 dimensions that has supersymmetry, but nevertheless, let's remember that it's n equals 1, or more invariantly, 32 supercharges. Okay? And Lilia also told you how to take this theory and compactify it on an S1 of some radius R. And the metric ended up looking like something like this. Right? Now, the radius of compactification, or if you wish to interpret this as a metric, to give an interpretation of this as the compactification radius will appear here as R squared. Okay? But that's very interesting because Lilia showed you how to compactify on an S1 and land on something that is called type 2A supergravity. The reason it's called type 2A is not just by chance, that also our string theory that we discovered in 10 dimensions was called type 2A. The reason they are both called the same is that the low energy effective action of type 2A, if you only consider the massless modes, gives you type 2A supergravity. Now, this theory has also 32 supercharges. But in 10 dimensions, that means n equals 2. That's the reason we have the 2. Okay? Now, why is type 2A and not type 2B? Can anyone tell me? Why did we get, or not we, but why you and Lilia got type 2A supergravity coming as a dimensional reduction of n equals of 11-dimensional supergravity and not type 2B? How could you have? That's right, it's not chiral. And why do we know that what we get is non-chiral? Well, the reason is that in 11-dimensional supergravity, we have a single Majorana spinor. And when we go down on a circle, how can you tell which one is right-handed or left-handed? You should get both. So from a single Majorana spinor in 11 dimensions, when you go down to 10 dimensions, the components, well, I don't know the notation that you guys were using, but suppose that you have, this is a gravitino in 11 dimensions. And when you go down, let's use these indices as the 10-dimensional indices, and this is as the 11-dimensional index, meaning the 11th direction. Some people like to say that, or some people like to say that time is 0, and you have 1, 2, 9, and 10. And then this one would be called chi 10. But it's up to you. I mean, well, right? As it is on the board, there is an inconsistency. So I should, I should make up my mind. What do you prefer? If I call this chi 10 Is that clear, what I'm saying? There are 11 dimensions here, but we usually call time 0. And we are compactifying this guy on a circle. So maybe I should call this mu the indices that go from 0 to 9, and then say that this is the last guy. Okay? I'll do that. Then write on the board, at least everything is consistent. So these guys, this single Majorana spinor, will come down to 10 dimensions, and it will be a full Majorana spinor. But a full Majorana spinor can be decomposed into 2 Weyl spinors of different chirality. So this guy will give us 2 Weyl spinors. Sorry. Yeah, 2 Weyl Majorana spinors of different chiralities. And this guy will give rise to 2 Gravitini. Okay? So these are the Dilatini and these are the Gravitini, different chiralities. So that had to be type 2A supergravity. Okay, this is something that people knew for a long time. But then, in 1995, there was this crazy suggestion. The crazy suggestion was the following. So you should be very happy because we're finally in the 90s. So we're in 1995. Okay? And then there is this crazy suggestion that says, well, we know that we have type 2A superstring theory. And what is the coupling of the theory? On the wall sheet, we have alpha prime. That's true, but that's our perturbative point of view, where we model every term in perturbation theory in the space-time as a full partition function on the wall sheet, and also there we have a perturbation theory. That's alpha prime. But in space-time, what is the coupling? We also discussed that. We call the coupling, we define the coupling to be e to the expectation value of the dilaton, right? So that was the string coupling in space-time. So if you're given this blackboard, what would you have said? Well, just connect this formula to that formula here. And you would say, well, isn't that interesting? It's as if the string coupling to the 2/3 was the radius of the 11th direction. Here is again the problem, okay? So, but we already decided to choose 10th as the 11th direction. So number 10 means the 11th direction, okay? Well, so the crazy suggestion is that there exists a theory in 11 dimensions which has a weakly coupled description around flat spacetime with lowest modes, those of 11-dimensional supergravity, and the same low energy effective action as 11-dimensional supergravity. So the crazy idea was to postulate the existence of such a theory, and such a theory was called M theory. Okay. Well, proposing that there is a theory in 11 dimensions that is consistent and that exists by itself is one thing. But another thing is to say that not only that, but that theory, when you compactify on a circle, will end up giving rise to type 2A superstring theory with this coupling. Okay? So the proposal is that there is this 11-dimensional theory, M theory, which if you compactify on a circle of some radius r, you will land on type 2a superstring theory with coupling even by this. So if you were wondering what the strong coupling limit of this theory is going to be, well, this conjecture tells you that the strong coupling limit has a geometric interpretation. It's actually growing a new direction. Okay? Well, why is this theory called M? That's an interesting question, but the most natural answer is the following. In 11-dimensional supergravity with Lilia, you also found that in the field content, of course, you had the metric, you had this gravitina, maybe you call it chi, but you also had somebody else. What was the extra field? The remaining field. Or that was it? You had to have something else. And that was a 3-form. Well, but we are now experts in gauge potentials. So whenever we see a gauge potential, we can immediately tell what is the kind of object it couples to. So we have a 3-form gauge potential. So it couples to what kind of object? That was only yesterday that we did all that. Oh, I know. Yeah, it's all my fault. Now it's A3. Right? It's a 3-form gauge potential. So it has to couple to something that has work volume, which is 3-dimensional, right? So it couples to a 3-dimensional object. But we agreed that we didn't want to write 3 as 3. We agreed that we wanted to write this as 1 plus 2, where this was the P, right? So this object couples to a 2-brane. Well, but a 2-brane is what we really call membrane, right? This is a membrane moving in space-time. So it's a 2-dimensional object in space. So it's actually a membrane moving in space-time. So this theory, whatever it is, contains a membrane, or we can call it an M2 brane, just to keep the tradition of calling P branes by the P. Let's just stick the 2 inside here instead of the EM. Okay? What's the magnetic dual of this object? It's a 5-brane. So the magnetic dual of this guy is an M5 brane. Okay? Very good. So now the first consistency condition that this crazy idea has to pass is whether we can give a meaningful interpretation to the objects we see here coming from the objects we see over there. So imagine that you have your M2 brane and you compactify your theory on a circle. So your M2 brane can do 2 things. Either the M2 brane can wrap the circle that you are compactifying your theory on, or it can just decide to hang around the other directions and don't do anything on that compact direction. Okay? So you can choose to wrap, or you can choose not to wrap. Depending on what it chooses to do, it will become a different object in 10 dimensions. So if it chooses to wrap, what is it going to be? What kind of object? From the point of view of the 10-dimensional theory. So you have this membrane, but one of the directions decides to wrap the circle. And if the circle goes very, very small, if it becomes very small, indeed, remember that all the description we know of type 2A, all the things that we have done in the course, are valid when the coupling constant is very, very small. If the coupling constant is very, very small, then the radius is very small. So from the point of view of the 10-dimensional theory, this membrane will look like a string. Well, in type 2A, we only have one string, right, which is the fundamental string. So this thing goes into the fundamental string. Or it should do it. So isn't that fascinating? So our nice little object in 10 dimensions that we have been quantizing and playing with, if this whole story is true, is really a membrane in disguise. It's a membrane wrapping a circle. Now, if it doesn't wrap anything, it will go into a two-brane. But the only kind of two branes we have in type 2A are D branes. So it goes into a D2 brane. Now, the magnetic dual of this guy, the M5 brane, being the magnetic dual, we were expected to do something opposite to what this guy does. In the following sense, remember that the fundamental string, we could also call it NS1 brane. So wrap or not to wrap? That's the question. So if you do it, if you wrap, of course, you get a 4 brane. But we only have in type 2A D4 branes. If you don't wrap, you get a 5 brane. But we only have one kind of 5 branes, which is the NS5 brane. So you see that the roles got swapped. The location of the NS and the D got reversed. Excellent. So what about the 0 brane, the 6 brane? Well, each one of those questions was a great paper. But we don't have time to discuss what they all are. So the 6 branes come from something that are called top-knot solutions, monopole solutions of the 11-dimensional supergravity. So this is just, so this whole story is just to motivate you to answer those questions. How about the D0 brane? How about the D6 brane? And yesterday, we also had that question of, what is this DA brane? Why don't we see it? Okay. Very good. But let's keep going here on this side. We know that there is something else here. There is a theory called type 2B. And this is in 10 dimensions. And yesterday, we argued that if you now compactify this on another circle of radius r, you get a new theory down here. And this theory is supposed to be equivalent to this theory compactifying a circle of radius 1 over r. So these theories in 9 dimensions, we can just call them type 2 theories. It doesn't make sense to say type 2A or type 2B because they are basically the same theory. So in 9 dimensions, the type 2 theories unify into a single theory. Okay? Very good. So that looks like a nice picture. So we're not going to follow the historical order. We are just going to use a lot of hindsight. Yes, a lot of I mean, but that's what one has to do when we have to do so many things in just 1 hour. Okay, you just have to find geodesics in history. But it's not completely crazy. You're given, suppose that now you're given this picture. Now, what's the next natural question to ask? Well, suppose that you have this M theory, or this theory, this 11-dimensional supergravity. Is there any other thing I can do to this theory? Can I compactify it on something else that is not a circle? Okay? So that's the next question we want to answer. So what's the deal with the blackboards here? We can just move this one. Okay, and this one, right? All right. Good enough. So what else? Well, take this theory and go down to 10 dimensions. Not on a circle, but when you look at the action, you say, well, there is a Z2 symmetry or a Z2 action that I can impose on the action that seems to give me something reasonable in 10 dimensions, or so that the fields do something interesting. Is a parity transformation in the 11th direction, the one that you are compactifying. You can try to apply a parity transformation and say, well, only the modes that are invariant under that parity transformation will survive when I go down to 10 dimensions. But what happens to the space when you compactify on a circle and apply that parity transformation? Well, people call that parity transformation, since it's just, if you apply it twice, you get the same answer. They call it a Z2. So this is a group, the finite group Z2. And what you get, S1 mod Z2, is nothing but, with a particular action that I have in mind, is nothing but an interval. Okay? So that sounds like a funny thing to do. We're compactifying this theory on a space that is an interval. Now, that's only the 11th direction. So if we were to draw everything else, what would it look like? Well, it would look like our interval, and at the endpoints of the interval, so anywhere inside the interval, we have a 10-dimensional object at every point. In particular, at the end, we will have walls that look like this. So these are 10-dimensional objects. And in the inside, we will have 11 dimensions, right? And the compactification has to do with the fact that the radius, or the length, maybe I should call it L, the length of this interval is what controls our compactification. If it's very, very small, then we're really only seeing a 10-dimensional theory. If it's very, very large, then in the bulk, in the middle, we only see the 11-dimensional theory. Yes?
Usually, for example, for the vector line, we divide Z1 by Z2, S1 by Z2. By identifying antipolar point.
Yeah, this is not that projection.
S1.
Yeah, this is not that projection.
So what exactly, how do we do that quotient? Oh, okay, okay. Yeah, perfect, thanks.
Okay, so you do that. You say, well, very good. Now you start asking, what does this Z2 action, how does it act on the fields? Once again. And it turns out to do something interesting. As I told you, it's parity, but it does act differently on the 10-dimensional components of the gravitino it acts as simple as a parity transformation on the 10-dimensional components of the gravitino, and it switches it acts with a minus sign on the 10th component of the gravitino. Okay? So when you go down to 10 dimensions, the only things that will survive in your theory are the ones that are invariant under this transformation. So in 10 dimensions, whatever this thing happens to be, it will have to be a theory that contains a single gravitino with plus chirality, right, because it's invariant under the transformation, and a single dilatino, which is K11, with negative chirality. Okay? So whatever we're going to get is a theory that only has n equals 1 supersymmetry, or n equals 1 is going to be an n equals 1 supergravity in 10 dimensions. So it's definitely not one of our type 2 theories. It's just one n equals 1 theory, and we don't know what it is. Well, the people who studied this, you might wonder why I'm not giving you references now. The reason is that the references will be in your homework. Okay? But the people who studied this were also experts in something else that has to do with field theory, which are called anomalies, in particular gravitational anomalies. And they realized that when you compactify this theory in this manifold, or in this space, the theory will not be consistent by itself. It will develop anomalies precisely at the end of the world, at the ends of the world. That's how they call them. So, and these anomalies end up being something that you can cancel. So due to anomalies, at the ends of the world, they realized that for this theory to be consistent, there had to be an n equals 1 super Yang-Mills theory living in 10 dimensions at each end of the world. And there were only two choices for the gauge group in order to cancel the anomaly. What were the two choices? So at each end of the world, you could have either a U1 to the 248. Here or here. Do you know any other group that has 248 dimensions? E8? E8 is one of them, yes. It turns out that E8 is the other possibility. So just from anomalies, they knew that that had to be the case. And by studying what happens to the membranes when they stretch from one side to the other, this theory has membranes, as we discussed, and just by studying the membranes and the anomaly that will also be induced on the membrane at the end of the worlds, they could show that these were not possibilities. Okay, so those were not possibilities. So whatever this mysterious theory was, it would have to be an n equals 1 supergravity theory, as we said here, and it would also have to have an E8 cross E8 gauge group with n equals 1 supersymmetry. Okay? But it's, yes?
Could you repeat why we got those gauge groups?
Why, sorry?
Why did we get those E8 or E1s?
I didn't quite tell you. All I told you was that they discovered that there were anomalies, gravitational anomalies, that had to be canceled. And the only way they could be canceled is if this theory somehow, remember, this is not a derivation. We don't quite understand what this M theory is, right? All we can do is to find consistency conditions for the theory to be reasonable, right? And if we discover that there is an anomaly, maybe we have to add a new sector in the theory. So the theory, if we had a fundamental description of it, it would tell us what it is. But the way we are discovering it is by saying, well, we know this piece. Now see if it's mathematically consistent, and we discover, oh, there is an anomaly, and the anomaly will kill the theory. So if the theory exists, there must be something that cancels it. Let's see what it is. So there were those two options, just from the point of view of the bulk. But from the point of view of the world volume theory of the membrane, you kill the U1 possibility, and that's the only possibility that is left. But now you should be a little bit disappointed, because you say, well, that means that we missed something in 10 dimensions. How come? There must be a theory in 10 dimensions that has this EA plus EA, and only has one supersymmetry. So it should not be a type 2 supersymmetry, a type 2 supergravity. Well, we go back to the drawing board and check what is it that we're missing. But that's not that easy to do unless we study T-duality a little bit more. Or better yet, instead of T-duality, instead if we do a little bit more of torus compactifications. In your tutorial, I think. So I think it was a tutorial and not a homework. In your tutorial, you study what happens when you compactify the bosonic string on R1, 24 cross S1 with a radius R. Say you study the closed bosonic string, and you said, well, all we have to do is to quantize the string, imposing boundary conditions of the form right? Where M was an integer, and it was telling us the winding of this string. So what the M is telling us that if this is a compact direction, in the M sector, we have a closed string that winds around the compact direction M times. So this was an integer. So I hope you remember that there was a condition on the momenta along that direction. You found something like P left squared minus P right squared had to be equal to N times M, where N was what? It was what?
The momentum was quantized.
Excellent, very good, very good. So the momentum was quantized because this is a compact direction, and the units of momenta that we have times the units of winding had to agree with this quantity. Okay. Now let's do a more general compactification. So what would be the more general compactification? It would be something where, people also like to call the compact direction. In this case, it was 25th, right? But so the only condition, the boundary condition that was modified was only for the compact direction. So people like to call the compact directions with an index I. The mu index is reserved for the non-compact directions. So we're going to call the compact directions I, and they will go from 1 to this, say. So we're compactifying on TD torus, which means D copies of an S1. Well, but now what could the boundary conditions be? We will have something that looks like this, plus 2 pi r. Now you can have anything. We want to allow here let's write something like m times ei. Okay? Is that the notation I want to use? Just a second. So let's throw here, yes.
All the S1s need to have the same radius?
No, they don't have to have the same radius. Right. But let's take them to have the same radius. Okay? So what I want to say is that we could also have something that looks like, let's actually introduce a different notation. Let's put all these vectors as if they were a single vector. Okay? And now, I don't want to erase this, so let me try to draw it here. Say we were just doing a compactification on a two-dimensional torus. So we can describe the two-dimensional torus as points in R2 so that if we have a vector E1 and a vector E2, some two vectors that you choose, you can declare that this will become a torus if you identify all the points if you identify any point with any other point that are related by a linear combination, by an integer linear combination of these basic vectors. Okay? So this point here will be the same as this point here because it's a linear, they are related by one unit of this vector. So these 2 points are identified. This point will also be identified with this point because it's related to that point. This one is related to that point by 1 unit of this vector minus 1 unit of this vector. Okay? So those are the boundary conditions that I want to impose here. So we want to say that points must be identified if they differ by any linear combination of the basic vectors. Okay? Is that clear? Is it clear why this is a torus? Right? Because if you walk in this direction, you end up here. Because this point is supposed to be equivalent to this because it differs by 1 unit of this vector. Okay? Now you just do it in d dimensions, and that's your torus. So for each one of these guys, we will have a p left I, and a p left, and a p right. P left I and a p right I. The generalization of this condition turns out to be that 1/2 p left as a vector square minus p right square is equal to the product of ni mi. Okay? This one, okay. Out of all the possible choices, this was okay, but it wasn't the optimal. I mean, of the 6 over here. Okay, so we have this. Now, there is already something interesting here. Well, this also took somebody very brilliant to realize that the natural thing to do is to actually put the 2 on the other side. When you put the 2 on the other side, of course, then that's not the only thing that you have to realize. But once you do that, the same person says, well, oh, that looks very interesting. Doesn't this look like the inner product of something that lives in 2D dimensions? So define a vector in R, D, comma D. And your vector, your new vector, will be something that has components P left, P right. And this thing will be nothing but the inner product of this object with this signature, where the metric in that space is 1, 1, 1, minus 1, minus 1, minus 1, D of them, and D of them. Okay? So consistent compactifications will correspond to lattices in RD, comma D that are even. Well, what's the meaning of even here? It's actually the factor of 2, which means that any 2 points in the lattice, right? So these vectors now define points in this lattice. So we now have this lattice. And the inner product of any 2 vectors, P and P prime, with this signature, right? So this is a lattice with this signature, has to be even. So that's the brilliance of the factor of 2. Now you can ask, well, can our string theory live on any space that is compactified on a lattice that has this property? Well, in the same paper, people realized that that's not the only condition. Quantum consistency requires one more condition. So let me call these P's elements of a lattice, or the lattice of points here. I'm going to call it gamma. D, comma D, for obvious reasons. It's a lattice in D, comma D dimensions. So we already know that it has to be an even lattice, but quantum consistency requires gamma to be equal to its dual. So it has to be self-dual. Are you familiar with the concept of the dual of a lattice? That's something you see in condensed matter all the time, right? The dual of a lattice. Good. This is no different than that. It's just that it's probably many more dimensions and with a different signature. Okay? Now you're giving a math problem. The math problem is finding all self-dual even lattices. And that will give you the possible spaces where your string theory can be compactified. Then when you have a math problem, what do? You go and ask your friends, your math friends, right? Then you go and you ask your math friends, and you tell them, look, for this physics reason, I need lattices that are even and self-dual. And then they will tell you, well, this is a well-known problem that was solved maybe not many years ago, but it's completely known what they are, completely classified. We can even give you something more general than what you want. We know what all even and self-dual lattices are of the kind D1, D2. And they only exist if D1 minus D2 is equal to 0 modulo 8. Okay? Then you say, well, D1 and D2 equal to each other is definitely 0 modulo 8. So great. So we can compactify. We know what the lattices are and so on. But then somebody stops for a second and says, oh, there is this thing that is bothering us. There is some funny theory there, right, which we don't know what it is. It might be a string theory, but how do we get it? We seem to have done everything we could. We had the closed string. The bosonic string is not even supersymmetric, so how can we get n equals 1 supersymmetry, right? This mysterious theory is n equals 1 supersymmetric. And we only have the type 2 superstrings, right? But now our math friends tell us that we don't have to keep the d's the same. They can be different. But remember, in the closed string, we have right movers and left movers. And do they talk to each other? Very rarely, right? The two sectors of the theory basically don't talk to each other. And now they are telling us, you see that each d corresponds to what the left movers and the right movers are doing, right? And mathematicians are telling you, well, you can do whatever you want as long as the difference is 0 modulo 8. So you can do something to the left movers different from what you do to the right movers. Well, you probably have figured it out by now, right? What is it that we want to do? We want to get this n equals 1 supergravity in 10 dimensions. So definitely we cannot start with a type 2 theory in 10 dimensions, because that would have two supersymmetries. We cannot start with a closed string, bosonic string in 26 dimensions, because it has 0 supersymmetry. So what do you do? So type 2s in 10 dimensions, too many supersymmetries. The bosonic in 26 dimensions, 0 supersymmetries. And now our math friends are telling us that we can compactify left movers and right movers and do different things to each other. Well, why don't you take the bosonic string and say you take the left movers of the bosonic string, of the closed bosonic string, and you compactify only that sector, okay, on gamma 16,0. You don't do anything. You only take the left movers. You don't do anything to the right movers. This one satisfies the condition. D1 minus D2 is 16, which is 0 modulo 8. Okay? And you take from these guys, you take the right movers. So from the right movers, you take our friends. And from the bosonic string, you take the left movers to be compactified on precisely 16 directions. So from 26, you go down to 10. So you will compactify this on T16 to go down to 10 dimensions. Okay? And when you do that, well, you have your oscillators, your alpha i's, and your alpha mu's, now in 10 dimensions. This theory, of course, has only n equals 1 supersymmetry, because we only have one of the two sectors, right? One of the two Ramon ground states. We don't have the same sector on the right-hand side. And then you go back and ask your friend, your math friend, well, you told me that you know everything about these even and self-dual lattices. So what are the possible even and self-dual lattices with D1 equals to 16 and D2 equal to 0? And then they will tell you, well, there are only, you're in luck. Because any other one, there will be an infinite number of them. If both these were different from 0, there would actually be an infinite number of them. But if one of the Ds is 0, there are only 2. There is only 2 lattices. You say, well, which ones are the lattices? Then they will tell you the lattices turn out to be the root system of an SO32 Lie algebra. So the Lie algebra, the roots form a lattice, right? That's what we were discussing yesterday. And that lattice turns out to be self-dual and even, just by chance. And you say, well, what's the other one? They say, well, the other one is actually the basic one that you get for 8 dimensions. And you put it twice, and you get the same answer. And you get something that is even and self-dual. So for gamma 8, you have only one lattice, which is the root system of E8. And if you want something in 16 dimensions, you just put it twice. So math friends, our math friends, knew that there were only these 2 options. Now, for every element in this lattice, we will get actually massless states corresponding to the simple roots of this system. And therefore, this thing will give us massless states which precisely interact as the gauge bosons of this or this. So we just discovered that we can have E8 cross E8 super Young Mills or SO32. Well, that's great. That's what we expected. But we now found something else. We found that there is another guy together with this one. Now, due to this funny way in which we constructed the theory, doing something to the left mover and something to the right movers, which was very different, these theories have been called heterotic. Okay? So just when we thought we could finish the course with this, because the strong coupling dual or the strong coupling regime of this theory would be M theory compactified on this, we now found this guy. Could that guy be an isolated object?
Could you please trace the other one?
Sorry?
Could you please trace the other one?
Oh, the other, yes. So to answer that question, the next thing that you do is to say, well, every time I compactify one direction, and I do the same thing to the left and the right movers, what I do is that I basically introduce one gamma 1, 1. Every time I compactify on a circle, and I choose to do the same thing to the left and the right movers, I produce something that has a gamma 1, 1. Okay? That's, in fact, what you found on the tutorial. That thing over there is a gamma 1, 1. Okay, so what do we do? So the top one doesn't work, right? Let's. Now you say, well, let me compactify the heterotic E8 cross E8 on a circle. After all, we were able to connect these 2 theories, type 2A and type 2B, when we did a compactification on a circle. So let's take heterotic. E8 cross E8 on a circle. Okay? So something must happen to our lattice E8 cross E8. Somehow we are imposing that in addition to this, we will also have a gamma 1, 1. So we are looking for something that is gamma 1, comma 17. Right? Remember these guys, or, well, it could really be 17, comma 1. Each one of these guys was a gamma 8, comma 0. And together, our math friends told us that, of course, they make up an even self-dual lattice with 16, comma 0 here. But when we compactify on a circle, we're supposed to produce a gamma 17, comma 1. And then we can go and ask again, well, how many gamma 17, comma 1s are there? Then they will tell us, but we already told you, there is an infinite number of them. Okay? Well, how do I classify it? So, and how do they look like? How do I know if they are special or not? Well, there is a trick to know that. And the trick is to draw, again, classify by Dinkin diagrams. You draw the Dinkin diagram of E8. So 1, 2, 3, 4, 5, 6, 7, and 8. Another one here. 1, 2, 3, 4, 5, 6, 7, and 8. And what this gamma 1, comma 1 does is to connect these two guys and make them into a single generalized Dinkin diagram. What it does is to connect these guys, or actually to connect the extended Dinkin diagrams of E8 cross E8 with a single node in between. So this was the connection. Now note that there is something interesting. Once you make that connection, can you spot inside here the Dinkin diagram of SO32? Is there any way to see inside that object a sub-Dinkin diagram that is the Dinkin diagram of SO32?
So we add string nodes.
What's that?
Did we add string nodes?
We added 3 nodes. I didn't tell you why. I told you that that's the way the gamma 1, comma 1 fits inside here. So the gamma 1, comma 1 fits inside here and completes this into a single object. Well, this is very tempting, right? This already looks like an SO Dinkin diagram. But in order to have SO32, we need 16 nodes, right? SO32 has rank 16. So we need 16 nodes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Wow, that was a close call. How many nodes are left? There are 3 nodes left. And then you get excited, go back and talk to your friend and say, look, I found this guy inside. Then they will tell you, of course, that's the other way of getting this lattice. You can start with gamma 16, or gamma SO32 cross gamma 1, comma 1, and complete it by adding 3 nodes. And they all form part of the same object, the same space of lattices, gamma 17, comma 1. So what do we learn? That when we compactify on a circle, these 2 heterotic strings become the same object, or belong to the same family of objects. So in 9 dimensions, there is only 1 heterotic string. Okay, and when you thought we were done, something else happened. So needless to say, I'm not pretending that you follow every single detail of what I'm saying. This is only motivation. I'm only trying to motivate you to do the third homework, which you still don't know what it is, but you will soon know. So this is just motivation for you. All right. Now that we have been trying to answer two questions. One, are these theories connected? And the answer is yes, of course. Okay? Maybe in a very complicated way, if you want to go from heterotic 32 to type 2B, you really have to do something, right? But we have been trying to answer another question. What is the strong coupling description of all these theories, right? So we succeeded with type 2A. We succeeded with heterotic EA cross EA, but we're missing two, right? What do you think happens to type 2B? The reason I'm asking is that you might be able to tell me now from the homework, from homework number 2. What's that? There is a duality. Excellent. There is a duality which seems to say that type 2B is actually self-dual. This theory might actually be self-dual under weak strong coupling duality. Okay, so this is what you guys were doing. So if that's the case, we're still missing what the strong coupling dual of this theory is, if there is any. Well, given the time, I don't think I'll try to motivate what it is. The motivation that I had in mind to do, I'll just tell you in words, was to start from this guy and compactify further down to 8 dimensions on an interval. Why is that? Because now I could try to take this guy and compactify on a circle. Now, through the chain of arguments, this theory will go down. Maybe we can just draw it, something like this. So this theory will go down to something on another circle. And this theory will go down in 8 dimensions on an interval to something. But following the chain of connections here, right, we see that these two theories should be connected or should be related somehow, right? You just have to permute the order in which you do things. But they are both M theory compactify on the same thing, right? On two circles and one interval. So somehow this should tell us how to connect these two theories, okay? And once you connect these two theories, you can try to go back. And when you go back, you should find that there are 2 ways of going up here. When you decompactify this, there should be 2 ways of going up here. And there should also be 2 ways of going up here, preserving the same amount of supersymmetry. So that will not land you on these theories, but that will land you on something else that lives in 10 dimensions, which is a theory that is called type 1. And has S of 32 as a gauge group. And these two guys are dual to each other as a strong weak coupling pair. Okay? So the last thing that I want to mention, so I wanted to have time to say that.
So type 1 is connected to the bottom ones, or?
Sorry? Well, yeah, so if you compactify this guy on an S1,
Yes.
and then perform T-duality on this guy, you land on something that is called, so you compactify on an S1, and you do T-duality. You land on something else that is called, it's called type 1 prime. And this type 1 prime can be seen naturally connected to the heterotic on S1. That will also be in the homework somewhere. Well, maybe you should worry. Okay, so here is the last argument that I want to make in the course. And it's the following. Take your heterotic string and take your type 2A theory. Okay? Let's see if we can do it without too much. Yeah. Now compactify this theory on a 4 torus. So what's the space of the remaining theories here? Of the theories that you produce, what is the possible space of theories that you can have? I told you that every time you compactify on a circle, you introduce a gamma 1, 1. So we started out with gamma 8 plus gamma 8. On a torus, we have to include a gamma 4, 4, and we end up with a space of theories that is somehow characterized by gamma 20, 4. Okay? Now, from the line of arguments that I told you here, we would like to find something where we could compactify type 2A and get something that is strongly coupled dual to this theory. But there is already a problem, you see, that this has n equals 1 supersymmetries, or it has more invariantly. So whenever somebody tells you n equals something, you should ask in how many dimensions. But since I don't want to answer that question, I can tell you that this thing has 16 supercharges. And if I compactify this on a torus, this thing has 32 supercharges. But there is also another problem. If I compactify this on a torus, the moduli space, or the space of theories that I can get, is only gamma 4, 4. It will not be gamma 20, 4. So once again, you go and ask your friends, and you say, well, is there any space, any geometric space that has 4 real dimensions that somehow can help me boost my gamma 4, 4 into gamma 20, 4? And it turns out that mathematicians have studied those. You need a space that is 4 real dimensional that has homology rich enough to give you, I don't know how much of that you know, but when you have an algebraic variety, you can study the homology, and the homology forms a lattice. And people have studied those very much. And they found, and they know of one that precisely has gamma 19,3 as the lattice of homology. You say, oh, so close to gamma 20,4. Well, you think a little bit more, and your friends will tell, well, this is something that you will have to figure out by yourself, because this is not in the math. This is something that has to do with physics. If on top of everything you add another 2 form for no reason whatsoever, well, for us there is reason. There is the Navier-Schwarz 2 form, which is a string. So if you also add the 2 form, the B-field 2 form in these directions, you can actually boost this up precisely to 20,4. So people started to consider the possibility that type 2A compactify on this strange space would be dual to this thing. So that space is called K3. So we're now compactifying. Sorry, our notation is that we're compactifying, going down on a space of real dimension 2. So this thing has complex dimension 2, real dimension 4. Now, this is not a nice torus, right? So you have to ask, what happens to the supersymmetries? Do I keep all supercharges? And it turns out, I'm not explaining why, but it turns out that this breaks half of the supersymmetries and brings you down to 16 supercharges. Where am I going to with this? Well, where I'm going with this is, that's a good question. Where am I going with this? Well, you should know where I'm going. I'm going to finish the course. But where do we want to, what should be the endpoint of this whole discussion. 4 dimensions, excellent, that's where we are going. We're going to 4 dimensions. So don't worry. Only 2 more to go, and we will get there. Very good. So now you have at your disposal a space where string theory seems to be happy to live on, which is this K3 space. You can have flat space-time times this K3 object, which, by the way, I think it's called K3 because they thought that it was going to be very, very hard to understand, mathematicians, even harder than climbing K2. Okay, so but I think nowadays it's very well understood. So we have another space that breaks supersymmetry naturally, and string theory is happy to live there. So why don't we compactify heterotic string on K3 instead? Okay? So instead of doing it on that space, let's actually do it here. Let's compactify heterotic on that space and go down to 4 dimensions. So in order to do that, we will first have to compactify on a T2 and then on K3, and we will finally be in 4 dimensions, right? How many supercharges are we going to have? Well, K3 breaks half of the supersymmetries, so we started with 16. We have 16 here, supercharges. And in 4 dimensions, we're going to get 8 supercharges. Now, how many supersymmetries means 8 supercharges in 4 dimensions? 2. Too bad. N equals 2 supersymmetry in 4 dimensions is way too much. N equals 2 super jump meals doesn't even confine in 4 dimensions. So we don't even get confinement. Imagine the standard model. So this is not satisfactory. But still, you can go back and play the game and say, well, is there a way of getting from type 2A something that will be the strong-weak dual of this theory? That would be interesting. If there is such a thing, whatever it is, whatever mysterious object, allow us to go down 6 dimensions, 6 real dimensions, or 3 complex. Well, people like to say whatever this thing is will have to break 1/4 of the supersymmetries, right? Because we have to go from 32 supercharges down to 8. Well, it turns out that such an object exists. Not only one exists, there seem to be a large number of them, okay? And these objects are called Calabi-Yau manifolds. Calabi-Yau threefolds. The 3 is this 3 here, okay? And when you compactify type 2A on this Calabi-Yau, you get something that breaks 1/4 of the supercharges. You end up with 8 dimensions. But now you see that we're done, right? What do we have to do to end the lecture and end the course?
Apply this to the heterotic.
Exactly. Now we find this space. We found these spaces where string theory is happy to live, and it breaks 1/4 of the supersymmetries. So why don't we forget about type 2A and compactify heterotic on that space? So if we break 1/4 of the 16 supercharges that we had at the beginning, we will go down to only 4 supercharges. And that's n equals 1 supersymmetry. So that's what we would want. So we end up in 4 dimensions with a theory that has 4 supercharges. And it has gauge fields. What kind of gauge fields are we going to have here depend on the Calabi-Yau threefold that you choose. So depending on this Calabi-Yau threefold, parts of this E8, cross E8 groups, will be broken, and some parts will be left over. So part of the goal is to find this Calabi-Yau compactification so that this group will be broken down to the standard model in 4 dimensions. So this is 4 dimensions. Okay? Very good. But I think it's fair to say that this was the state of the art already, as I said, in 1995. So I hope that you realize that this is basically the end of the beginning. Okay? So you guys, if you want to explore this theory, I hope this course was a helpful way to start. Okay? And Pedro will tell you something that happened, I think it was in 1997. So the ADS-CFT duality, now I don't remember. Or, oops. Yeah, I should remember when that happened. Very good. So Pedro will just help you go 2 more years. Well, but many things have happened since then. Okay? Very good.